So first thing, depending on the time, I might not talk about eventually dendric words. So I'm sorry about that. I'll see if I have questions on that or not. But yeah, so I'm mostly going to talk about dendric words. Before I really start the course, let me introduce some notations because I will forget later otherwise. So A will be an alphabet. I think that's pretty classical. And I will consider small x, made it a little bit bigger, which is the easiest way to see it is maybe to see it as a two-sided sequence on the alphabet, but you can also see it as a one-sided sequence without problems at the beginning, or as an element of a shift space or whatever you want. But essentially this is a sequence. And I always assume that every letter of A appears in X, so this is what I write like this. So this notation here is for the language of X, so all the words that appear in X, and the 1 here means that the words of length 1. So this means that all the letters of A appear in my sequence. Okay, so this is the assumptions I will make all the time. Oh, maybe I should. Okay, and so my goal today is to introduce dendricity, so dendric sequences, and to explain the link with other families of sequences that you may know. Okay. And I'll try to do a diagram on this right blackboard of all the relations between all the properties. Okay, so it all starts with, let me write it here. So it all starts with Sturmian sequences, which, based on yesterday, I think most of you have heard of, but maybe not all of the interesting properties I will want. So what are Sturmian sequences? Essentially, we say that X is Sturmian if it is aperiodic and its factor complexity is n plus 1. So the number of length n words that appear in my sequence is exactly n plus 1. And by a famous theorem, this is the minimal possible factor complexity if you want to be aperiodic. Okay, so these are classical sequences. And as a direct consequence of this definition, well, you can see that if you take a word of length n, there is always at least one way of extending it to the right to obtain a word of length n plus 1 that is also in your sequence. So this would be of length n plus 1, right? But since when you go from n to n plus 1, the factor complexity increases by 1, that means that there is exactly one word of length n which can be extended in two different ways on the right. Okay. So let me formalize this. So we write some definitions. So if W is an element, a word that appears in my sequence, I will say that ER of W is the set of letters that can follow W in my sequence. Okay, so these are the letters that I can see here to the right of my word and still stay somewhere in X. And these are called right extensions. Okay. Okay, so that's, I think the name is pretty natural. So the way of extending W on the right is the right extensions. And of course, you can do also left extensions. Now, am I right? So left extensions would be exactly the same, but on the left. So these are the letters such that they can precede W in my sequence. Okay. So these are the left extensions. Yes? Of the drawing, yeah. So it's to explain that going from complexity n to n plus 1, you can see a link between the words of length n and the words of length n plus 1. And the link is that you take a word of length n, there's always a way of adding a letter to the right and obtain a word of length n plus 1. And here, because of the complexity, there is also a word of length n which can be extended in two different ways. Or in other words, this is a characterization. So X is Sturmian if and only if for every n there exists a unique word W of length n such that the number of right extensions is equal to 2, and all the others, their number of right extensions is equal to 1. WU. Okay, because the number of words needs to increase by 1 when you go from n to n plus 1, then the only possibility is that you have one word that splits in two, has two different possibilities, and all the other words have a unique way of being extended. Okay, and same goes for the left. So there is such that the number of, here you can replace it by number of left extensions. I'll write it differently. I'll write it like this. For exactly the same reason, for every word of length n, you have at least one way of adding a letter to the left of it, and this creates a word of length n plus 1. But since your words of length n plus 1, you have one more than the number of words of length n, there is exactly one word which can be extended in two different ways on the left. Is that clear for everyone? Yeah, okay. So this is an alternative characterization of being Sturmian, and of course there's aperiodicity in there also. Okay, now a third way of characterizing Sturmian sequences, and we saw it briefly yesterday, is through rotations. So I will not give the proper definitions, but I will give a drawing. So it's also a definition, but differently. So take circle, okay. You take a parameter alpha, an angle basically. And what you do is you have a dynamical system that for each point, maybe not x, for each point, you will shift it by this angle alpha. This will be the image of z, right? And of course, if your point is there, you shift it and you go over there. So always the same angle alpha. So you have this dynamical system. And now if you cut your system here, not here, here, okay, into two parts. So you have this orange part and then this blue part. And now what you want to remember is, okay, I take my point z and then I apply this rotation, and sometimes it will end up in the blue part and sometimes it will end up in the orange part. And I'll say, for example, that if it ends up in the blue part, I will encode that by a 0. And if it'll end up in the orange part, it's a 1, right? So to my point z, I can associate a sequence. Actually, it's a two-sided sequence, but I can also reverse my transformation. And so this dynamical system is a rotation. And so this is actually not a definition, it's a proposition maybe, better. If alpha is irrational, but of course depends on how you define alpha, if it's the angle or if it's the length of the arc there. But basically, if it's rationally independent with the total, the full circle transformation, then the codings of the elements Z are Sturmian sequences. Okay? So if you take your point Z, you look at the sequence of 0 and 1 associated with it, well, it's a Sturmian sequence. And it is a characterization in the sense that every Sturmian sequence can be obtained like that for some alpha and for some point. Okay, so these are 3 of the ways of seeing Sturmian sequences. There are many others, but I won't have the time to go into that. And these are essentially the 3 I'll be interested in. Are there any questions so far? No, okay. Okay, so this was the starting point, Sturmian sequences. Oops, let's go all the way up because it will go there eventually. Will it stop? Okay. Okay, so now these sequences are been studied a lot since Morse and Leun's work, and of course it led to some generalizations. And the first generalization is, well, the first I'll talk about, is one we heard about yesterday, and it's the Arnoux-Rosie sequences. Arnoux-Rosie sequence. Or we also say that these are called also strict epistromian sequences. And what is an Arnoux-Rosie sequence? Well, you take the second characterization of Sturmian, which is all the way up there, and you adapt it to larger alphabet, because the goal here is to have larger alphabet, because of course Sturmian is only 2 letters, but we want larger alphabet. So for all n, there exists a unique U of length n, such that the number of right extensions of U is actually some constant k, which will actually be the size of the alphabet. And the number of extensions of any, or maybe I took W there. Or was it? Was it W? Yeah. So let's keep the same. So this is W, and this is U. One for all U different. Okay. And this time you also have to add the condition on the left, and the same, but for the left. So there exists a unique W of length n, such that the number of left extensions of W is equal to the same constant, and for any other word of the same length, the number of left extensions is exactly 1. Okay.
Question: does the k depend on n or is fixed?
No, the k is fixed, and actually the k will be. So k is fixed, and is actually k is the number of letters in the sequence. Because if this has to be true for n is equal to 0, and for n is equal to 0, of course, there's only one word of length 0, which is the empty word. And so it has to satisfy this, so its number of extension has to be equal to k. And that means that k must be the number of letters in your sequence. Okay? So these are so-called Arnold-Rosie sequences, and they come from the second characterization of Sturmian sequences. And the most famous example, we saw it yesterday, is Fibonacci. Okay, so it's the sequence generated by this morphism. Okay, so this is one way of generalizing Sturmian sequences, and it preserves a lot of properties of Sturmian sequences, namely in regards to palindromes and other things we'll talk about today or maybe tomorrow or Thursday, I don't know. So this is one generalization. And another generalization comes from the other point of view, the point of view of rotation. So what you do is you see rotations as, okay, let me try to do a drawing that looks like something. So this would be blue, and then this would be orange. Okay, and this would be the other way around. This is blue, and this is orange. So this rotation over there, I can also see it like this, because every time I take a point Z here, it is mapped by translation to this other point, and then I can reproject this other point here. So this would be the image of Z. Okay. So this rotation, if you cut your circle and flatten it, then you can see it as a piecewise translation, where you have two pieces, which are intervals, and of course you translate them so that they don't overlap in the end. Well, if you did that with two intervals, you can do that with more than two intervals. So now generalize this, so take similar construction, but this time you cut into more pieces, something like that. And then you rearrange these pieces. So maybe I'll put this one over there. Now I'll put this middle one there, then the small one, then the short one. So I don't know if I'll have enough colors for that, but let's try. So this would be there.
The lengths are preserved.
Yes, so this is a translation, really. So I preserve the length of the intervals, and I translate them so that they don't overlap in the second copy. So let me take other colors. So this little one here goes here. And then, do I have a fourth color? Yellow, maybe yellow. This will work. Yeah, this works. Okay. And now the idea is exactly the same. You can do a dynamical system with that. So if you take a point in here, for example, it will be translated into the corresponding point in the other copy. And then we map it also. So this is maybe not the best drawing because I took a point which was very close to its image. So we can do it again, and now I have a point here at the start of the yellow interval, so it will be translated here, and then reprojected there. So this would be the second iteration of my transformation on my point. And we keep going, okay? And so exactly as for the rotation, this is a dynamical system, which is, I'll abbreviate it like that. Don't worry about the R for now, but IET means interval exchange transformation. Okay. So this is interval exchange transformation. Yes?
So if every Arnold-Rosie sequence can be associated to a pair alpha and then a pair, like a vector with a length
Sorry, every word can be?
Every sequence, every honor rosie sequence.
No, so this is another generalization.
Oh, no, sorry.
So yeah, this is a generalization, and now we're doing another one,
Oh,
and we'll see the link between the two just after. Okay? So now you have a dynamical system, which is an interval exchange transformation, and you can also code. So I don't know, let's say orange is 0, 1, then 2 for red, and 3 for yellow. And I can again associate with my sequence, with my point Z, I can associate a sequence. So this would start with 2, then 3, then 1, and so on. Okay? So these are called, so for each, to each Z, we can associate a sequence, and this would be called the coding of Z. Okay. Okay, so one generalization of Sturmian sequences is Arnold-Rosie sequences, and another generalization is codings of our IET. And now I'm claiming that these two generalizations, maybe it's too big, I'll do it smaller because I still need to add more things also. Up. So these are Arnold-Rosie sequences. Here we have codings of regular interval exchange transformation. And of course, these two generalizations intersect, because if you take k equal 2, or if you take only 2 intervals, well, you get the Sturmians back. So in the intersection, we'll find the Sturmian sequences, and in fact, we only have the Sturmian sequences. Okay? Now, let me try to convince you of that. Okay. So for Arnold-Rosie sequences, we know exactly how their extension behave because that's the definition. Now, can we understand how the extensions behave in interval exchange transformations? Okay, I'll do a slightly simpler drawing for that. So we only do 3 intervals. Let me do a small one there, big one. Okay. Not much. Okay, so this one is here, and then the other 2 are swapped. Okay, so how can we understand extensions in there? Okay, let's try, for example, so I'll say this is 0, 1, and 2. Let's try, for example, to understand what are the letters that I can put to the right of 1. Okay? Well, if I see 1 followed by some letter A, that means that at some point, the Z I'm looking at will move somewhere, and at some point it will be in 1, and the next iteration, it has to be in A. Okay, this is exactly, okay, so maybe I will take another point because this is very close to the cutting line. I'll take this one. So right away you see on this drawing that A can be equal to 1. Okay? And more generally, you can also see that if I take this point there, this means that A can also be equal to 0. Okay, so here A is either 0 or 1, and it cannot be 2, because if I'm in the blue part, at the next step I will be in this portion of the interval. And so the only possible letters for after are the ones that cross this section, and so these are 0 and 1. Okay, so how do we see right extensions of 1? Well, we look at the bottom copy of the one interval and look at what are the top intervals across it that intersect it. So in some sense, for right extensions, what you should do is look at the bottom copy of the interval and check the top interval that intersect. Okay, it's okay for everyone for this ID. Of course, here I only did it for the letter 1. And I say look at the bottom copy of the interval. But what if I want to look at the letters that can be to the right of some W? How do I do that? Well, actually, I'm not going to go into the details, but there is also a small interval that corresponds to W. Okay? And so what you should do is it's exactly the same, but this time you look at the bottom copy of the small interval corresponding to W and check what are the top interval that correspond to it. Okay? So it's exactly the same. And the important part is that the interval corresponds to W gets smaller and smaller the longer W gets. And so if W is long enough, then this small interval will only cross at most 2 of the top intervals. And so that means that if X is the coding of an RIT, then long words have at most 2 left extensions, and the same goes for the right, of course. Everything is symmetric. Okay. Questions on that? No? Okay. So now you can see clearly that the only way of having a sequence which is both Arnold-Rosie and coming from an interval exchange is to have exactly k equal to 2, and so as to have something Sturmian. Okay? Okay. Ah, no, not that one. This one? Yes. Yes?
Is it true because there was 3?
No, it's true for general, no matter the number of intervals, this property will be true. This is really because this construction works exactly the same. You have to look at the copy of the interval, but on the bottom, and look at what it intersects on the top. But since these intervals become smaller and smaller, at some point the diameter is smaller than the diameter of the smallest of your starting interval. Okay, just a minute more. Okay. So now we saw 2 ways of generalizing Sturmian sequences, and these 2 ways have some common properties. Even though they don't really intersect, other than in the Sturmian case, they have some common properties. And one of the property is that if my sequence X is Arnold-Rosie or a coding of a regular interval exchange transformation, then its factor complexity is given by this formula. Okay, so remember, I assume that all of the letters of A appear in X, otherwise this would be false, of course. Okay, now just clearly see that if you only have 2 letters, well, this gives you n plus 1, so you recover the factor complexity of Sturmian words, so that's already a good sign. Now I will try to convince you of this, but only for Arnold-Rosie. For interval exchanges, it's a bit more technical. But let's try to do a short intuition on that. Okay. So, how do I say that? Okay, so as we saw, for Sturmian, what I did is that I had the factor complexity and I said, okay, well, let's look at how it increases when I go from n to n plus 1. And since it's increased by 1, it tells me that I have exactly one word that splits. So actually, it's easier to look at what we call the first difference. So this is defined as first difference of complexity. Right? So we want to compare the words of length n plus 1 and the words of length n. But a word of length n plus 1, so if this is of length n plus 1, I can always cut it into two parts, a word of length n and then some last letter. Okay? So actually the words of length n plus 1 are, for each word of length n, I have as many different words of length n plus 1 as I have letters possibilities on the right there. Okay? So from that you can deduce that this difference is actually the sum over the words of length n of the number of ways you can extend it on the right, w, right? This gives you the number of words of length n plus 1. For any word of length n, you count how many letters you can put there to form a word of length n plus 1. And since we're subtracting the complexity in n, just do minus 1. No questions? Okay. Now, if I did it on the right, I can also do it on the left. So I can also say that my word of length n plus 1 is first a letter, then a word of length n. And so this exact same reasoning will give the formula, but for the left. Okay. Now, let's look at the case. So this is general. Like I didn't assume anything on x for now. This is a general formula. Now, what happens in the case where x is an Arnold-Rosie sequence? So if x is Arnold-Rosie, I know that among the words of length n, one of them has k extensions and all of the others only have one extension. So only one of them will contribute to this sum, because all of the other will give me 1 minus 1, and will contribute to k minus 1. So my difference of complexity is equal to k minus 1. It doesn't depend on n or anything else anymore. Okay, and now it's a simple computation to show that if the difference of complexity is constant equal to k minus 1, then the factor complexity is, well, k minus 1n plus 1. Okay. It is an affine function, and k here, as I said, it's just the number of letters. Okay. So that's the factor complexity of Arnold-Rosie for interval exchanges. The proof is very different, but I won't do it, and actually we'll obtain it as a consequence of other stuff. Okay. We can go a little bit further in this and actually look at the second difference, so the difference of the difference. Okay, and this is another proposition. If you look at the second difference, well, what you obtain is a kind of similar formula. So you take the sum over the words of length n, but this time you have to sum something different. So something which I haven't defined yet, I will define it soon, minus the number of right extensions, minus the number of left extensions, plus 1. Okay, and what is that something? That something is the number of what I call just extensions, or bi-extensions, or two-sided extensions, or whatever, depending on my mood, Okay, and so these are the pairs of letters that can surround my word. So A, W, B in my language. Okay, so I look at ways of extending W, but on both sides. So these are the extensions. Okay. Oops, and let me just say something. So this value here, this is what we call, so this thing here, I won't repeat it. This is what we call the multiplicity of W. Okay. And the idea is that, well, if you know the multiplicity of all of your words, then you know what is the second difference of complexity. So in some sense, you know the second derivative. And you can recover the complexity by knowing that the complexity at 1 is 1, at 0 is 1, and at 1 it's number of letters. Okay. Okay. So of course there are multiplicities that are more interesting than others. So we'll say that W is neutral if its multiplicity is 0. It is weak if its multiplicity is negative, and strong if the multiplicity is positive. Okay, so we distinguish three types of words depending on their contribution to the second difference of complexity. And now what is interesting for us, well, if you have to look at it a little bit, but we saw it here that for Arnold-Rosie sequences, the first difference of complexity is constant. So that means that the second difference of complexity is 0. And in fact, it is because in an Arnold-Rosie sequence, every word is neutral. Okay, so this has a name also. So, oops. We say that X is neutral if all of the words in this sequence are neutral. W is neutral. Okay. And so property, proposition, well, X being an Arnold-Rosie sequence implies that it is neutral. In fact, X being a coding of an interval exchange transformation implies that it is neutral. I'm not proving that. And of course, if X is neutral, then all of these are equal to 0. So the second difference of complexity is 0. So the first difference of complexity is constant. And so the complexity is affine. And so if X is neutral, then the complexity of X is that one. Right? Questions? No questions?
Slightly
Yeah.
bigger, please.
Oh, slightly bigger? Oh, sorry, yes. Okay. Okay, so what it means is that in this drawing we can add 2 circles. So these will be the neutral sequences. And even bigger, we have the sequences of complexity. Oops, right there. So P of x over n is this formula. And neutral, I realize I wrote it very small, so let me write it bigger. Yes? Yeah, because I don't have this place inside. Yeah, it should be there. But yes, there is, but yeah. Okay, so we saw two generalizations of fermion sequences, and we saw that they had some combinatorial properties in common, and especially these are properties that are related to counting stuffs. Either we're counting the extensions or we're counting the number of factors, so the complexity. But they also have some common properties that are not counting stuff, but more structural properties. And so this is where the dendricity comes, and I will switch Blackboard. Okay, so the idea is that we counted the extensions, but we can also look at how they interact in some sense. Let me put the other one back up. It's coming, it's coming. Okay. Okay. So, let's Okay, so this is the third part. Yes.
So in the case of binary alphabet, your entire class is
Yeah, everything shrinks down. Yeah. So this is the third part, and this is where I introduced the main object, which is dendricity. Okay, so I said we want to look at the structure of the extensions, and the way to do that is to realize that actually, where is it? Somewhere there? The real extensions, so the two-sided extensions, sort of define a relation between left extensions and right extensions. And the way of representing a relation is to do a graph. So this is what we call the extension graph of some word W. So if you understood the idea of the relation, well, you shouldn't be surprised, but well, what will follow? So, graph, whoops. So it's vertices. The set of vertices is the disjoint union of the left extensions and the right extensions. And there is an edge between some A, which is a left extension, and some B, which is a right extension, if they are related. So if AB is an extension. So let me do an example. So I will do an example for Fibonacci. Okay, so what does the Fibonacci sequence look like? It's something like that, and then 0, 1, 0, 2, 0, 1, 0, and so on. Okay, and let me look at the extension graph of, I'll take the empty word, I will do this. Okay, so what are the left extensions of the empty word? So, well, what are the letters that I can see to the left of nothing? Well, everything. So, all 3 letters are left extensions. Okay. And they are also all right extensions. So, these will be the left extensions of my empty word, and these will be the right extensions of my empty word. Okay, and now how do I connect these? Well, I checked whether 0, empty word 0 appears. Well, it does, it's here. So I connect these two. I check whether 0, empty word 1 appears. It does here, for example. Then I will quickly run out of colors, but anyway. Then 0, 2, it appears. Then 1, 0, it also appears. Yeah, I don't have colors anymore, so I'll do it like that. Okay, but for example, 1, 1 does not appear, so I don't connect 1 on the left and 1 on the right. And so the only one left is that one. Okay. Okay, so now for each W, I can associate some kind of graph. And well, here you already have the graph of the empty word for Fibonacci. And you can see that there are 2 particular vertices, these 2, right? And this is normal, because this 0 on the left tells us that at length 1, there is only one letter that can be extended in 3 different ways on the right, and that's that one. And all of the others have only one possibility on the right. And this tells you that at length 1, there's only one word that can be extended in 3 different ways on the left, and it's that one, and the others only have one possibility. So you really see in here the property, the definition. And more generally, so this is the sequence of the example, let's say. So in Fibonacci, the extension graphs are there's only 4 possibilities. So there is this possibility, only one vertex on the left and one on the right. There is the possibility where you only have one vertex on the left, but then you'd need 3 on the right. Then there's the mirror of that. So only one vertex on the right and 3 on the left. And then there's the one we just saw for the empty word, which is that one. And these are the only possibilities in Fibonacci. These are the only possible shapes. And now, okay, I'll quickly say something about interval exchanges before moving on. Okay, so for interval exchanges, well, this idea that we had there of describing the extensions tells you that essentially if you write the extensions, okay, so let me focus. So if you write the right extensions in the order of the top, so in the top order, so this one, and if you put the left extensions in the bottom order, so the order of the intervals on the bottom copy, so this would be this order, then your extensions, your lines here, do not cross. I don't know, they can look at something like that, or maybe you have not as many vertices, but what matters is that they don't cross because of this observation on the top. Okay? So what you can see here is that in both cases, the graphs are very particular. So for Fibonacci, the graphs always look like that, and more generally for Arnold-Rosie, they will always look like that, but maybe with more vertices. And for interval exchanges, they can be represented in a way that the edges don't cross. And a common property of that is that in both cases, these graphs are trees. So they are connected and no cycle. Okay, so this is the reason for this definition. So we'll say that W is dendritic if its extension graph is acyclic and connected. Okay, so it is a tree. And yeah, I don't need much more than that. Okay. And quite naturally, we'll say that the sequence itself is dendritic if all of the W are dendritic. Okay. And now you should be slightly convinced that both Arnold-Rosie sequences and codings of interval exchanges are dendritic. And if you know a little bit of graph theory, you know that when you have a graph which is a tree, then you have a link between the number of vertices and the number of edges, right? And that link is precisely the fact that the number of edges minus the number of left vertices minus the number of right vertices plus 1 is equal to 0. So it's exactly the fact that, let me just write it here. If X is dendritic, then X is neutral. And so in particular, it has complexity like that. So up, we can now add dendricity in there. And, oops, not there. It's there. So this is dendritic. Right, so generalize both of these generalization of term sequences, and it preserves the combinatorial property of counting, but it also preserves something else, and that's what we'll see in the next courses. Okay, that's it for today.